Thank you, Oliver. Slightly different talk, but the flavor is we're going to look at some machine learning models. So I guess my title is very long. The key idea is I'm going to look at GANs and tell you some of the information theoretic foundations of it. I'm going to also connect them to loss functions, but take this perspective of what is the divergence you should pick for GANs to minimize, for example. Right, and this is joint work with Monica, who's here, and Gautam, who was my postdoc, is now a professor in India, and Kyle, who started this work as an undergraduate student, who's now graduating in the master's. So GANs, generative adversarial networks. I'm sure everybody knows about it. ChatGPT doesn't use it, but this is still the mother of all models that are generating synthetic data, right? So I'm going to focus on this. There's some nice mathematical structures here to understand. So the key idea of GANs is that you have two functions and they operate in an adversarial manner. You take real data, you feed it into one of the functions. That function is actually a discriminator. It's going to actually make a decision between real data and some other data that's fed to it, which is synthetic data. And the synthetic data is generated by another function that operates on, say, distributions coming from a lower dimensional latent space, right? So the discriminator's goal is to distinguish between the real data and the synthetic data, and the generator's goal is to take that feedback from the discriminator and improve its synthetic outputs, right? My postdoc Gautam really likes this. He calls it a game between a counterfeiter and police, where, of course, the job here as a counterfeiter is to win against the police, right? So ideally, the discriminator should not be able to distinguish. All right. So GANs are used, but even if you're surprised, ChatGPT does not. It uses larger diffusion models, but GANs have been used to do a lot of things, especially if we go look at what NVIDIA does and so on, and including using for protein synthesis. All right, so let's dive into the math a little bit. GANs were introduced by Goodfellow and his collaborators about almost 10 years back now, and what I'm going to call the vanilla GAN, right? So you stare at this. I mean, we figured out that there's a game being played between the discriminator and a generator. So mathematically, that becomes an inf soup over two functional spaces, right? The G functional space of the generator, and we're going to parameterize this by some theta, and the D functional space of the discriminator parameterized by some omega, right? What matters is that this is a zero-sum game. They both want to minimize and maximize the same function, and this function, if you look at it, this is what Goodfellow et al. Picked. It has this form, where this is the output of D is the output of the discriminator, and you put a log in front of it. It looks like a log loss rate, it is. And that is averaged over the samples from the true data. And one log 1 minus that is averaged over the samples from the generated data, and or really from the latent space of the generator. Okay. All right. So for this setting, D is actually a output between 0 and 1. And so if the discriminator outputs 0, that means it, the discriminator outputs 1, that means it's real data. If the discriminator outputs 0, that means it's actually fake data, right? So ideally, you want this output to be 1/2. Right? Okay, so if you look at this optimization and you start with the inner optimization, which is the supremum over this function, it's not so hard. You can, law of unconscious statistician, you write it out in terms of the distributions on the X itself, and you minimize this, you get an optimal discriminator of this one. Now we're in a universe where all functionals are possible. So this would be the best functional for the discriminator. You plug that back in, what you get that the generator minimizes over is simply twice the Jensen-Shannon divergence between the true distribution and the generated distribution minus some term constant. Okay, right? And for those who've forgotten, Jensen-Shannon is just asymmetric divergence. Right? Okay. So you stare at this, you go, hey, yeah, this is a divergence we all know. It comes from KL. So if you can do this, why can't we try and minimize a different divergence? So in fact, the answer to that question was formulated by Novazin et al. In 2016, where they said, well, you don't need to have GAN, which is now the vanilla GAN. You can have an F GAN, which minimizes any F divergence. So how do I write it in that value function form? You take an F divergence and you can write its convex conjugate, and then you, so you can take the take the F divergence definition and you plug it back in, you get this form for the value function of the objective that the two players minimize and maximize. Okay. All right. So, so depending on the F you choose, you can get back the vanilla GAN, or the Hellinger GAN, or the total variation GAN. Okay. All right. So these were the GANs sort of people are interested in. In fact, Novazin's paper has all kinds of Fs and all kinds of corresponding GANs, right? Following all this, there were work by others, the W-GAN, Wasserstein GAN that many of you may be very familiar with. It was introduced not just as another F-GAN, it is not an F-GAN, but to actually address some of the problems with vanilla GANs. There have been other GANs introduced that really take different divergences, such as the Cumulin GAN, the Renyi GAN, and so on. Okay. All right. So what I'm going to do in this talk is really tell you that this value function, at least in the context of divergences, can be written in terms of loss functions. Okay. So you stare at this for just a moment and go, yeah, it looks like log loss, right? In fact, it looks like I'm taking data samples and I'm minimizing. It looks like some kind of risk minimization, right? So why can't I stick any other loss in there? A loss that actually maps to 0, 1, what we call in machine learning as a class probability estimation loss, okay? A soft loss, right? So the a loss operates on two things: the ground truth y, which is binary in 0, 1, and y hat, which is an estimate of y over 0, 1. Okay. All right. So what we want to restrict, if we want to map this to some loss form, is to restrict that this symmetric loss is actually this loss is actually symmetric in the following way. All right, so what am I doing here? I am now replacing log D of W by some loss. And I have a negative here because in classic, the discriminator is a classifier. So it's minimizing some loss. And since we've written in this game form as a supremum, so I just take a negative. Okay. All right, so the interesting thing that comes from this GAN part is that you're minimizing on the real samples, that's 1 here, the data from the real, and minimizing this partial loss for the synthetic samples from the data from the synthetic. Okay. So in machine learning literature, this L1 and L0 will be typically called partial loss. Okay, so but for the GAN setting, you do want it to satisfy one constraint that that when the discriminator is half, you should get the best performance. Right? That's when it cannot distinguish. So we want the loss to satisfy this constraint. Okay. And convexity of this loss function suffices to do that. Okay. So I'm going to give you our first result that we have, which is that this min-max optimization that I showed you, in any symmetric, so symmetric for this loss as I defined, reduces to minimizing an F divergence. So I started with losses, and what I'm telling you is that the inner optimization, the supremum over this loss formulation that I have, is going to become an F divergence such that the overall optimization is going to be an infimum over an F divergence. Okay. So you give me a loss, it is equivalent to minimizing an F divergence. You give me an F divergence, a symmetric F divergence, there exists a loss model for it. Okay. It's actually super cute, and the proof really comes from this very nice paper by Nguyen, Wainwright, and Bartlett, a good decade or so back. You've got to write this loss in a margin-based form. I don't have time to go over it, but it's really a cute result. Okay, so what this tells me is that there exists a loss for any F divergence, symmetric F divergence that you want to minimize. Okay, and sometimes it's easier to work with loss functions. All right, so an example of this is a kind of loss that I've been working on for a while. It came out of some really nice work with Oliver, which was motivated by work by Aaron Wagner on maximal leakage. Oliver and I was staring at his paper, and then I was like, oh, well, we should think about general expectation guessing. And he goes out for a day, comes back with the formulation, and then it took me a year to figure out we can put it in some machine learning context, right? Those who know Oliver here are smiling. So here's our loss, right? Its alpha is a parameter, slightly different alpha from Cynthia's, in the morning, but so I've written this more in a machine learning setting. Y is either 0 or 1, so one of the terms will be 0, right? So y hat is your estimate, which is between 0 and 1. Now, instead of just taking y hat, which will give you log loss, by the way, if you take, be a little bit careful. Instead of taking y hat, you take y hat raised to the power 1 minus 1 over alpha. Okay, all right. So if I plug this loss in to this model, what I'm going to tell you is that this loss itself for alpha equals 1 recovers log loss. For alpha equals 1/2, it recovers the exponential loss. And for alpha equals infinity, it actually recovers the soft 0,1 loss. Okay. So correspondingly, the divergences then become the Jensen-Shannon divergence, the Hellinger divergence, and the total variation distance. All right, so this is a loss function we were obsessed with, and we wanted to understand how it works in the GANs setting. And so in the GANs setting, this loss function, so the inner optimization, if you put this alpha loss in, gives you what we now call the Arimoto divergence. Arimoto came up with this divergence and came up with this loss itself in a completely different context of understanding what happens to probability of error when the rate is over capacity. And then Weider took it over and did a lot of stuff, and he named it the Arimoto divergence. So the Arimoto divergence looks like this. This is symmetric. All right. So, and for different values of alpha, you recover some of the known results. Okay. So the second result that I'm going to tell you is we're still in the setting where we can express all functionals, but now we're going to ask the question: if you get more and more samples asymptotically, is there any difference in these divergences? Should I pick a particular loss or a different loss? Should I consider a particular divergence or a different divergence, right? So this, Kamalika and her collaborators have this really nice concept of equivalence and convergence. And they say two divergences are equivalent if for a sequence of probabilities and the second probability measure being fixed, right? If one goes to 0 asymptotically, if and only if the other goes to 0 asymptotically, okay? And what they showed, Arzhowski and his collaborators showed is that the Jensen-Shannon divergence is equivalent in convergence to the total variation distance. Okay? And then Chowdhury et al., Liu et al. Showed that there is in terms of convergence, the Jensen-Shannon, the Hellinger, and the total variation are equivalent. Right? What we did was we showed that all alpha divergence, the Arimoto divergences are equivalent in convergence. Now we can actually generalize this result to say that all symmetric F divergences are equivalent in convergence. Okay? So if you give me the sequence, this is exactly what I've written. And it actually simplifies some of the earlier proofs because it's based on this really cute result by Feldman and Osterreicher. It says that any F divergence, symmetric F divergence, is bounded above and below by functions of the total variation distance. All right, so that is the second result. The third result that is also somewhat theoretical is moving to a slightly different worldview. In reality, we cannot have all possible functionals for the generator and the discriminator, right? Oftentimes, all these models are trained on neural networks, and neither do you have infinite number of samples from the real data. You could generate infinite number of samples of the synthetic data, but they're only as good as the model you train on. So you can look at a setting where you have finite number of samples from both. So in this setting, now we have empirical estimates of the real and the generated distribution, right? And this immediately leads to the following problem, that you cannot get a precise estimate of the divergence when you only have finite samples. In fact, Arora et al. Showed that when you have finite number of samples, you are lower bounded away from the true divergence by a certain amount for, say, the Wasserstein GANs, for the F GANs, and so on and so forth. So what they said is effectively, we need to have a better estimate of how close these two distributions are to one another. You still want to estimate how good a GAN is, but you no longer have infinite number of samples or infinite capacity of your models. So what they did in this setting was they introduced a notion called neural network distance. And what that is the following. All right. So this is their definition. And it says there's this estimate coming out of the discriminator, right? DW, say it's between 0 and 1. Now you take this and you take this as a supremum over all possible generative discriminator functions, right? So in the most general setting, you have a supremum inside, right? That's what leads you to a divergence. That's the game. The generator is trying to minimize and the discriminator is trying to maximize a particular function, a value function. We no longer can get that divergence because we're in the finite sample and the finite capacity setting. So in this setting, we define this as a proxy for divergence. And so this proxy, they call it the neural network distance. Okay, all right. So this is now going to be used to evaluate how good is your model that you learned. Okay, so first thing we can do is we can take that neural network distance and generalize it as follows. You can take it for any loss function that you have. And keep in mind, the loss function is of this form, just to keep it simple and not have a negative sign. I've just written it as phi here, right? So we're going to generalize it from their setup to the following, okay? So this is just a generalized neural network distance, right? You plug T in there, you get back the Aurora's neural network distance. Okay, so what have we done here? This is the function we're going to use to claim that this is a measure of distance between two distributions. Okay. All right. So here's our third result, and it says the following. Suppose you have n samples of real data and m samples from your latent space that you're generating, and m random samples in your latent dimensional space. So this is what you use to train your GAN, and you use a partial loss that is actually Lipschitz, right? So L phi Lipschitz, yes. So then with high probability, this is the kind of, so here's the setting. What we want to understand is that the reality is you only have estimates of these two distributions from the finite samples, right? Based on these estimates, you can take this neural network distance, you can minimize this over your neural architectures that are possible, and you will get the best generators model. So if I take this generators model and I plug it in to this neural network distance that we have defined and compare that to what you can do if you can allow for all possible generators here over the true distributions, then this distance, this is what's called a estimation error. So this estimation error can then be bounded by the following quantities. Okay. All right. This was first studied for the neural network distance presented earlier by Yingbing Liang and her collaborators. So we sort of generalized this for the for any CPE loss, and in particular, these constants that you have here really depend on the neural network parameters. Okay, I apologize that I've left out a lot of details. That makes it hard to understand it fully, but in the interest of time, I'm sort of going to do that. Okay, so this proof actually builds on their work, but it also leverages because we're, so in Liang's work, the D can be anything over the reals. In ours, it's actually limited to 0 to 1. So then we use a contraction lemma on Rademacher complexity. And we can also plug in our own loss function, which is L alpha, the alpha loss. And we can get order optimal results when alpha is infinity. Okay, which means we can get lower bounds which match the upper bounds in square root of, and making some assumptions that you have lots of samples for the generated data and you have a ReLU activation. I apologize that I haven't given you all kinds of details. But okay, I want to focus most of this talk on understanding what should be the right value function you should use in a GAN. Like, is it enough to use vanilla GANs? What are the problems in training GANs? Can that be addressed using loss functions? Okay, so let's go back. This is our game between, it is a zero-sum game, but keep in mind that the min-max or inf sup is not equal to sup inf. So This can be solved in one shot, which is what I told you about, right? This is the optimal discriminator. You can put any loss, and for example, I'm going to look at alpha loss from now on, which induces the alpha GAN, as we call it, right? So this is your optimal discriminator. What really happens is when actually alpha goes smaller and smaller, you actually get a very cautious discriminator, which I will clarify in a moment. On the other hand, as alpha goes to infinity, you actually get a discriminator that's very confident, which makes a maximum likelihood estimate on the output. Okay, makes a hard decision. All right. Stop me at any point in time if you have questions or if you didn't follow anything I said. Even then, you should stop me. But so here are some major issues in training GANs, which is why some people like the diffusion models better. Here are 4 problems that I'm going to list out in training GANs. The first one is what is called vanishing gradients, which means when you start out, you're starting out with some 2 neural network models, you're starting out with some arbitrary distribution, typically Gaussian for the latent space of the generator, and you get all this real data. The discriminator is very confident. It can distinguish between real and generated data, right? So what happens is that when the discriminator is that confident, you take those log functions, the generator's loss is little to no gradient when the discriminator is very confident. As a result, the generator function cannot move very well. So then it cannot respond and it doesn't learn, right? So that's one problem, that's a training instability. Another is, even if you could fix that problem that I just talked about, you can get the gradients of the generator. If the generator were able to move towards the real distribution, as it approaches the real distribution, it can have exploding gradients. I'm going to show you examples of all this, but this is yet another problem, okay? These and a combination of other problems can lead to what are called mode collapse, where the generator gets very happy that it learned a few modes. It can fool the discriminator on these modes, and somehow it doesn't move out of them to learn other modes, okay? And a problem that's not talked about too much, but is quite a serious problem, is that as with all neural networks, hyperparameter initialization matters a lot. How many epochs should you train it for? In fact, it's been observed for vanilla GANs that the longer you train, you can learn the distribution and then just fly away from the distribution. You get completely unstable at some point. That's because of these exploding gradients, right? So it's very dependent on the initial seeds, and in particular, the number of the learning rate and the number of epochs, okay? And in fact, the learning rate affects the convergence, and if you choose the loss function appropriately, you can reduce this dependence a bit. All right, so I'm going to use a toy example to highlight some of these instabilities. So on this plot on the left, you see the real distribution that's in blue. It's a Gaussian with a mean -3 and variance 0.5. And you're starting off with this distribution, right, which is mean -1 and same variance. Luckily, you started the same variance. Just looks easier, right? So any loss function you use, whether it's alpha equals 1, which is your vanilla GAN, or any other alpha here, this is your optimal discriminator. Let's assume that you have enough capacity that you can achieve this optimal discriminator. Okay. Now, how does this optimal discriminator look? So on the left, keeping your focus on the left, this is what the optimal discriminator looks like when alpha is equal to 1, which means you're using the vanilla GAN. The discriminator, remember, it takes values from 0 to 1. It's very confident for the real data, and it's very confident, and it's 0, right? And if you look at the generator's loss of for the same alpha, this is what it looks like. It has really 0 gradient where you are, and then the gradient sort of decreases. So if you're here, which is where you started, you have no gradient to move anywhere. Okay? So now what if I changed alpha a little bit? So I'm going to increase alpha because I'm just moving in some particular direction. Keep in mind, as you increase alpha, the discriminator gets very confident. Remember, at the limit, it actually is a maximum likelihood discriminator. It's going to pick the most likely point. So here's your alpha. And so you see that you still have vanishing gradients. Okay, it's just that it doesn't decrease, it actually flattens out here, right? And the limit of alpha infinity, literally they overlap, and you get the discriminator gets very, very confident. Okay, so why don't we tweak alpha and go in the other direction? So alpha 0.5, I start getting some gradients here, right? So alpha 0.2, I get even more gradients here. Why? Because the discriminator is less confident. Because the discriminator is less confident, it allows the generator loss to actually move. Okay. Right. So in fact, you put more mass here, that in turn converts to having non-zero gradients here. Okay. All right. And so the limit alpha equals 0 is almost irrelevant, but yeah. So here are the pluses and minuses of tuning alpha. Okay. So if you tune alpha less than 1, you get more gradient for the generator, as I just showed you, right? Because the discriminator is less confident. You really need that at the beginning of training. Okay. You create a better, smoother landscape. But another side effect is that you may, if you look here, your gradients get steep very quickly, unfortunately. So you may provide too large of the gradients for the generator, especially when it starts approaching the real samples, which is what was happening in that plot. Okay, so this will result in too much movement because as you get closer and closer, you really can't, and you just get repelled away from the real data. Okay, all right. So this was not a problem that we observed. In fact, the vanilla GAN, Goodfellow et al. Know about this problem. So the way they address this problem in their setting, right? Forget all these, they don't know about alpha loss, they're in this setting. How do they take care of this? They said, well, let's just tweak this generator's loss. The reason it has 0 gradients is the way this function works. I'm going to throw out, I'm going to change this loss function. Keep in mind, if you change the generator's loss, it's no longer a zero-sum game. Okay, but that's what they did. They have what is called this it's called the non-saturating loss, because in the previous setting, the generator's loss was saturating and you had no gradients. So they proposed a non-saturating loss, which is big. Now it's just, instead of log of 1 minus d, it's minus log d. Okay. All right. So the problem is this still suffers from mode collapse. And it still suffers from the problem that when you get closer to some real points, you can get repelled. Okay, and it's very sensitive to hyperparameter initialization. All right, so we can ask the question, why don't we just use this alpha loss? I mean, we've been talking about it, it provides some interesting divergences. Why don't we plug that in? All right, so what we're going to do now is we're going to compare the non-saturated setting of the vanilla GAN with a non-saturated version of the alpha loss. Okay, so now we're in this, what I would call a non-zero sum game, because the discriminator and generator are optimizing different functions. Okay, go back to the same toy example. All right. So alpha equals 1, except now the generator's loss is different. So instead of having vanishing gradients, you actually start having high gradients. All right. If I make alpha larger than 1, my gradients don't blow up so much. Okay. On the other hand, if I make alpha less than 1, which gave me all this great, ability to move to the real data, unfortunately, I have more vanishing gradients. Okay, perfect. All right. That'll still work. Okay, so what I want you to take away is the following. Making alpha smaller allows the discriminator to be less confident and gives you gradients at the generator's initial points. On the other hand, if I take the non-saturated version of the discriminator's loss, it can also have a problem of exploding gradients. Okay, so this is just what I said. So can I ask the following question? Can I combine a less confident discriminator with a more stable generator loss? So what I'm going to do is I'm going to generalize this different objective game that Goodfellow themselves came up with by changing the generator's function to do something a little bit more general. I'm going to use a different loss function, alpha loss, but different alpha for the discriminator and a different alpha for the generator. And I want to make it clear that this kind of dual objective GANs is not our idea. There have been others who have looked at it, but what I think we've been able to do is to correlate it closely with training instabilities, besides the least squared GAN, which also did that. All right. So I'm going to sort of stop here because it's a plug for the poster that my student is going to give. So here's our new game. It doesn't have the same objective for the generator and the discriminator. They're two different objectives. Each one uses this value function that uses different losses, different alphas. Okay. The optimal discriminator is going to be the same because this is just optimizing that function. It's just now that is alpha D, and then you get a you get a different divergence here, okay? So we can actually do a lot of theory on this, go to Monica's talk. We can also obtain estimation error bounds, and we've tested on some really nice data sets, synthetic and publicly available. And the story we have, and we did something that I've not seen in the literature, and correct me if I'm wrong, we really trained over hundreds of seeds. I've almost not seen this anywhere in the GAN literature, okay? And over hundreds of seeds, what we can show is like much better robustness to training, all right? So summary, we have a nice way of connecting various divergence-based GANs to loss functions. And we can show that many of these symmetric F divergences are very equivalent in convergence in theory. What really matters in practice, you have finite samples, finite capacity, what kind of bounds can you give on those? But to me, I think the most interesting is that what is the right F GAN you should pick? What is the right divergence you should minimize? One way to look at our work is to say that we give some operational interpretation to these Arimoto divergences, looking at them through the lens of the discriminator as a classifier and how it affects training instabilities or stability. Stop right there, and there are all these papers you can look at.
Questions from Lalitha?
Yes, Matthew.
So I think one of the things I like is you have a very clean parameterization as a function of alpha. Does it make sense to schedule alpha during training?
Alpha is a hyperparameter.
That's right, but as you train your GAN, some of these issues they don't show up at the same time, right?
Yes.
So does it make sense to schedule the alpha?
Yeah, you could. It just makes it that much harder. In fact, the larger the images, we've been looking at only at images that you train on. You'll start seeing that the discriminator's function matters the most. The generator can be at 1, it's going to do fine. The discriminator's function matters the most. We've been thinking about adaptive, but it's not clear to us that we need to do that because we're seeing a lot of stability when we make the discriminator less confident. Because you think making the discriminator more confident as you train is better, but these GANs can very quickly move away from a mode when you do those things. So keeping the discriminator less confident really helps. But making the generator, I mean, in the generator's context, it's not about more confidence or not. It's really about what is the divergence and whether you have enough gradients to move. So you don't want exploding or vanishing. So that's a very fine line there. Yes.
Several other maybe heuristic approaches people have proposed to deal with mode collapse, like unrolled GANs. And I think, again, I don't know the latest in this topic, but there was people talked about Wasserstein GANs and how they were better than the vanilla ones in terms of mode collapse. So, so you can view this as, change the loss function, and then this is like a fix for mode collapse. And then on the other hand, you can view algorithmic innovations you could do while training to deal with mode collapse while not changing the loss function. So is there sort of a middle ground in between where one could use, some sort of hybrid training strategy, but at the same time, maybe play with the loss function itself?
Right. So to the best of my knowledge, Wasserstein GAN is also a different loss function. In fact, so every GAN has a set of problems. I think adversarial models inherently have instabilities because of the gain. So you're correct about that. I think to come back to your question, can you keep maybe vanilla GAN and change algorithmic methods? It only goes so far, to the best of my knowledge, which is why the Wasserstein GAN came in the first place. The problem with them is now they have to be one Lipschitz, which means they either have to clip the gradients or regularize the gradients. That has their own set of problems. And others observe mode collapse in them. I'm sure if somebody takes my word, they'll observe mode collapse. I don't know. There must exist a data set for which it's very hard to, there are so many real problems with GANs. Right now, FID score is the Frechet inception distance is the only one we know how to look at images, and it brings them down to some common latent space, assuming an existing model which acts as a transformer in some sense. And then you compare those scores and see how close they are, which is what Monica will show you tomorrow. But is that the only metric? We don't really know how to evaluate synthetic data against real data. There's some very fundamental questions.
Okay, let's think Lalitha again. Steps.
Yes, for the reception. There is a wonderful